Hello and welcome to the third of the lectures in this week 8 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last two lectures, we have looked at fuzzy rules as fuzzy points, and hence the interpolativity of the obtained function as a mapping from the spaces of fuzzy sets on X to fuzzy sets on Y appeared to be a good measure of correctness. We have seen, while trying to explore interpolativity in the case of a single CISO rule, we have seen that a couple of functional inequalities play a role, and also the algebraic structure of residuated lattice comes into picture. In this lecture, we will see the role of residuated lattice is not over. In fact, if anything, it has just begun to appear, and we will make use of the richness of this structure quite a lot in proving a lot of results related to desirable properties of a fuzzy inference system. And in this lecture, we will concentrate on fuzzy relational equations, especially the solvability of fuzzy relational equation with respect to the compositions that we have seen, namely that of the sup-T composition and the in-phi composition. Of course, we also need to understand how interpolativity is related to the solvability of fuzzy relational equations. That also we will see in this lecture. Well, a quick recap of what we have done in the previous lecture. So this is the framework in which we are dealing with. It's an FRI. If you were considering a single CISO rule, and for the composition we either consider sup-T or in-phi composition, we have seen what we call the TF conditionality played a role in obtaining interpolativity, and in the case of the BKS inference scheme, what we call the IF conditionality, a functional inequality of this form, seems to play a role in ensuring interpolativity. We have also seen this is in some sense a special case or a generalized case of what is known in the literature as T conditionality. Now, we have seen that one solution for this equation, inequality, comes from the family of R implications, especially when the T that we consider, the T norm that we consider is left continuous. And this led us to revisit the residuated lattice structure. What's a residuated lattice? It's a set L endowed with a few operations and constants such that L with respect to the meet and join and the bound 0 and 1 is a bounded lattice. With respect to the star operation, it is an ordered commutative monoid with identity 1. And finally, the star operation and the arrow operation, they form an adjoint pair. What does that mean? They satisfy this residuation property. We have seen that if we consider T norm and the corresponding R implication, they actually satisfy the residuation property if T is left continuous, and hence this entire structure becomes a residuated lattice structure. When we looked at residuated lattice structure in one of the earlier lectures, the early part of this course, at that time we were interested in making sure that with respect to the set of fuzzy sets, we were able to obtain as rich a structure as possible, mirroring what happens in the case of classical set theory. Now you will see here in the rest of the lectures throughout the course the power of residuated lattices in ensuring many of the desirable properties that we expect on a fuzzy inference system. So we have seen the importance or richness of residuated lattices in the context of theory in coming up with good structures with some properties. But now we will also see how these properties, this myriad of properties that residuated lattices have, how they are going to impact in applications by ensuring that the inference systems that we have considered have some nice and desirable properties. Well, even when we discuss the need for residuated lattice, we saw that it has a lot of properties. A couple of them we had listed out. You might recall these are some of the properties that we have listed out. If we look at the properties on the second line, in fact, they are effectively some special cases of what we consider or what we have introduced as TF conditionality and IF conditionality. So if you consider this as the T-norm, then this arrow is the corresponding residuated operator, and if you consider the arrow to be the corresponding residuated operator, which is the implication, then star could be the operation from which you had obtained the arrow. So this actually once again shows that perhaps it is good to stay within the framework of residuated lattice structure. So in that sense, we will explore FRIs for multiple seesaw rule case in this context, where the operations T and IT are actually coming from a residuated lattice structure, which means, of course, T is left continuous. Now, how is studying interpolativity of FRIs in some sense equivalent to studying the solvability of fuzzy relational equations? Let's revisit one of the examples that we have seen in an earlier lecture. So now we have a couple of rules, single input, single output rules, and we have seen that if you use a Gödel implication for obtaining the relation and max for aggregation and the sub decomposition, we see that given these two rules, A1 implies B1 and A2 implies B2, these are the relations that you obtain using this operation F. Now, if you aggregate them, this is the relation R you get, and we wondered about its interpolativity properties. We saw that if we gave A1 as the input, then A1 composed with R, we actually obtain B1. However, when we gave A2, this was not the case, because we could not obtain B2. Now, what does it mean? We have A1 implies B1, A2 implies B2. What we want is a single R such that when we gave A1 to R, then we obtained B1, and when we gave A2 to R, we obtained B2. We want a single R, and we see here this R does not seem to make the cut, which essentially implies that if we put the set of antecedents on one side, note that we are considering these as row vectors, and perform the composition, then what we are expecting is in the corresponding rows, the corresponding consequence. So now this entire thing can be looked at as studying this fuzzy relational equation, where Q is known, P is known. These are coming from the antecedents. One way to look at it is that way. And what we are interested is in obtaining this R. So how should we obtain the R? That's the question we are asking. So this is much like the matrix equations. Given A and B, we want to find an X such that AX is equal to B. So here we are given Q and P, and we are interested in finding an R. And this composition, of course, we are in the second. For us, our interest is from the point of view of fuzzy relational inference, which means we are going to talk about CRI and VKS inference, which essentially means we are either talking about sub T composition or in-phi composition. Well, let's look at some properties of these fuzzy relational compositions. This is the sub T composition. We have seen in one of the earlier lectures when we discussed fuzzy relations that if Q1 is less than or equal to Q2, then if you pre-compose with another P, then what we see is this is the inequality we have, we retain. It essentially says that it is monotonic in the second variable, of course, because of symmetry of the T-norm, underlying T-norm that we use. It can also be shown it is monotonic in the first variable. However, if you look at the in-phi composition, if we take IT to be the residual implication of a left continuous T, since we want to discuss in the framework of residuated lattice structure, the rest of the properties we will discuss when T and IT are related to each other as a residual pair, which means T is a left continuous T norm and IT is the corresponding residuated implication, the R implication obtained from T. So let's fix this. Then what we can see is, in the second variable, the inf IT composition is monotonic. However, in the first variable, it is anti-monotonic. Of course, once again, this stems from the properties of the implication, the R implication, which is a fuzzy implication, which is mixed monotonic in nature, decreasing in the first variable and increasing in the second variable. Of course, not in a strict sense. Now, what is interesting is, in this setting, if Q is a fuzzy relation on X cross Y, R is a fuzzy relation on Y cross Z, and P is a fuzzy relation on X cross Z, then these are some properties that we can prove. Note that here it's a nice mix of sup T with inf I composition. Of course, we should always remember we are discussing in the context where T and IT are coming from the residuated structure, which means T is a left continuous T norm and IT is its corresponding R implication. We have seen similar inequalities as properties for general compositions, but these are some special properties when we consider T and IT to come from the residuated lattice structure, and we will see how these inequalities will help us in discussing the solvability of fuzzy relational equations. We will, among these four inequalities that we have, we will pick up a couple of them and try to prove them. We will pick perhaps the first and the third one because the variables do change and so do the inequalities. So allow me to copy this. So we need to prove P is greater than or equal to Q inverse. Since we have fixed the T and IT to be coming from the residuated lattice structure, just to avoid cumbersome notation, we will not indicate the T or I over the symbols circle and this left triangle, but that will be understood in the context. This is what we need to prove. Note that P is a function from X cross Z to 0, 1. Q is from X cross Y to 0, 1. And R that we consider is from Y cross Z to 1. Now this is what we need to prove. So now if you want to prove this, note that P acts on two values X and X0 and Z0. So we need to show this is greater than or equal to Q circle Q inverse for arbitrary X0 from X and Z0 from Z. This is what we need to prove. Now, let's write the right hand side as U of X0 Z0 is equal to Q circle Q inverse delta P X0. Now let's expand on this. So this is sup T composition. So what we will have is supremum. Now remember, Q is from X cross Y. So before that, perhaps one thing that we should ensure is this. Remember, Q is from X cross Y. Q inverse is the transpose, so it is from Y cross X, and P is from X cross Z. So now if you see this entire U is actually from X cross Z to 0, 1, and P is from X cross Z to 0, 1. So dimensionality wise, we are very much in the clear. So let us expand this. This is supremum. Q is over X cross Y. X and Z are fixed. So supremum over Y coming from Y. Q of X0, Y star Q inverse Q Y, So now, once again expanding this, it's not y star. Now this is the in-phi composition, because I is the R implication occurring from the corresponding T. We are using just the infix notation, so that notationally it's easier to see. Now not that, we have to write this as Q inverse implies P of sigma y. Q inverse is from y cross s to 0, 0, 1. So which means this variable here varies over x. This is what we have. Now, let's do a similar algebraic manipulation as we have done in the previous lecture, where we considered the kernel of A separately, the support of the kernel of A separately, and the rest of them separately. So we could write this as supremum over y of x0, y star. We will divide this into two parts. The part where in t is not equal to x0, Q inverse y comma t implies P of t comma z0. The part where t is equal to x0, which is Q inverse y comma x0 implies P of x0 comma z0. Is exactly like how we have done in the previous lecture. So all we are doing is, as t varies over x, we will consider for all the t which are not x0, and when t is equal to x0, we are considering separately. Now, if you look at it, supremum of star over and here, we know that infimum of these two things is always smaller than this. We know that A and B is less than or equal to A and B is less than or equal to B. So, using this property here, what we can write this is, and supremum is monotonic over this, so this is less than or equal to supremum y element of y Q of x0 comma y star Q inverse y comma x0 implies P of x0 comma z0. Now, this is equal to supremum over y, as y runs over the domain of y star. Look at this, Q inverse of y comma x0 is nothing but the Q transpose. So it is essentially Q of x0 comma y implies Q of now, if you take this to be alpha, this to be alpha, and this to be beta, so what we have is alpha star, alpha implies beta. Now we know from the residuated lattice it is essentially A star, A implies B is less than or equal to B from the residuated lattices, which means we could write this entire thing as less than or equal to supremum over y element of y P of x0 comma z0. But note that the variable that runs is free here is running over the domain Y, whereas here the arguments are actually fixed x0 and z0, which are from different domains, which means it has no bearing on this value. This means this is x0. So what we have proven is, we started with u of x0, z0, which is this value, and we have shown that this is actually less than or equal to p of x0, z0. And since we took x0 and z0 arbitrarily, what we have actually seen is this property, first property, which is p is greater than or equal to q sub t composed with q transpose inphi composed with p. So we have seen, notice one thing, this is the equation that we need to understand. This is essentially TF conditionality or T conditionality, because if you consider the T norm and this as an implication, it is the T conditionality in the setting of residuated lattices which has actually helped us in showing this inequality. Of course, we have not seen the use of this inequality, which we will see presently. We will take up one more inequality to prove, and then we will go into discussing the solvability of fuzzy relational equations. Let's consider the third inequality. Allow me to just write it is r less than or equal to q inverse q sub p. Now once again, let's look at the dimensionality. R we know is from y cross z. Q inverse, q is from x cross y. Q inverse is from y cross x. R is from y cross z. So now, if you look at it, it is from y to z, which means dimensionality wise we are doing fine. So now let's start once again here. So R acts on some arbitrary y0 element of y and z0 element of z. So now we have seen that the same thing happens here. So once again, let's look at u of y0, z0 to be equal to q inverse q transpose at the point y0, z0. Let's expand this once more. So now what we have is infimum q inverse. Notice it is from y cross x to 0, 1. So that means it varies over x. Q inverse of y0, x implies q circle r of x, now this is q inverse of y0, x. Let's once again expand this. This is supremum over. Remember, q varies. Q is a function relation over x cross y. So now x is fixed. It is the y that will vary. So supremum p element of y, q of x comma t star r of t comma z0. So this is what we have here. Once again, we will split this q inverse y0, x implies supremum over t coming from y, t not equal to y0, q of x comma t star r of t comma z0 join with, at that point t is equal to y0, x comma y0 star r of y0 comma z0. So if this close this bracket and also. Now notice that for an implication A implies B or C, it is increasing in the second variable. So this is always greater than or equal to A implies B, also A implies C. So using this, we can say this is greater than or equal to infima x element of x q inverse of y0 comma x implies the quantity in green. Well, we do a similar thing as before. If you look at this, this is Q inverse, which is Q transpose. You could also write this as Q of x comma y0. This implies Q of x comma y0 star R of y0 comma z0. Once again, if you were to look at this as an alpha, alpha implies alpha star beta. You might readily recall this looks like the IF conditionality, which we know is greater than or equal to beta in the case of residuated lattices. So what we obtain here is that this is actually greater than or equal to x element of x R of y0 comma z0. Once again, the running variable is x. It has no bearing on the arguments that R acts upon, which means this is equal to R of y0 z0. Now note that y0 and z0, they are actually arbitrarily chosen elements from y and z. So that means what we have shown is this quantity is bigger than R of y0 z0. Essentially we have shown that this inequality is valid. We have seen the inequalities 1 and 3. The inequalities 2 and 4 can be proven similarly. Now let's look at how to put them to good use. Let's discuss the solvability of fuzzy relational equations. Now once again, Q is a fuzzy relation on x cross y, R is a fuzzy relation on y cross z, and P is a fuzzy relation on x cross z. And let's look at a system of fuzzy relational equations where we use the sup decomposition. Now, if you consider the set of all fuzzy relations over y cross z, then with respect to the usual component-wise ordering and the max and min operation, we see it is a bounded lattice. The matrix with all ones is the top element, the matrix with all zeros is the bottom element. Now, let us indicate by this S circle the set of all relations R coming from fuzzy relations over y cross z, such that for the fixed Q and P, Q sup decomposed with R is equal to P. So that means given a Q and P, we are picking all those R's such that Q circle R is equal to P. This is the interesting result that we have. If your T and IT, they form a residual pair, that means the T norm that you use in the sup decomposition, if it is a left continuous T norm and if you consider corresponding residuation of it, the following are equivalent. What does it say? This space, which is essentially the solution space, means given Q and P, all those fuzzy relations R and y cross z which satisfy this equation, that is non-empty if and only if this particular relation R cap, which is given as Q inverse in IT composed with P, is a maximal element of this set. So it's a very interesting result. It says that the solution space is non-empty if and only if this relation that you obtain from Q and P itself, much like in the case of invertible matrices, how we obtain X as A inverse B. So it says that in such a case, this relation that you obtain, of course, by using sup inf IT composition between the transpose of Q and P, this relation not only should be an element of S circle, which means not only should it solve this equation, but it should also be a maximal element of this space. What do we understand by maximal element of this space? So if we consider the solution space, an R star coming from the set of all possible relations on y cross z, it is a maximal element of S circle if, first of all, it should be a solution to this equation, and if there exists some other solution R dash, then this R star is not smaller than that. Note that it's a maximal element, it is not a maximum element. So if there can exist other solution, but however, no solution can be greater than this. So this is the result that we have. Let's prove this result. Towards proving this result, we will make use of these two inequalities which we have actually proven, 1 and 3. So now what do we have? We have S0, which is set of all R from f of y plus z such that Q circle R is equal to P. Now the result says that if S0 is not equal to 5, if and only if R cap given like this is a maximal, let me just say it's maximal in S0. So we need to prove two things, that it is a solution, this R cap is a solution, and it is also the maximal solution. One way is very clear. If R cap is a maximal element of S0, then it is also an element of S0, which means it is a solution for this equation. It essentially means S0 is not empty. So let's prove 1 implies 2. So let's assume that the forward direction S0 is not 5. This implies there exists an R in S0, which implies Q circle R is actually equal to P. So this is what we are doing. First, let's prove that R cap is greater than or equal to this R. Now, look at this third equation. We know that for any R, this is true. R is less than or equal to Q inverse Q circle R. But now, what is Q circle R? Because R is the solution, it is P. This is Q inverse P. But what is Q inverse P? Q inverse delta P. This is nothing but R cap. So what we see is, for any R which is a solution, R is less than or equal to R cap. That means, if R is a solution, R does not definitely dominate R cap. But however, we do not know whether R cap itself is a solution or not. So, let us prove that R cap itself is a solution. That means, Q circle R cap is equal to P. This is what we want to do. Now, look at the equation number 1. So now, Q circle R cap is equal to Q circle Q inverse delta P. But now if you look at the equation, the inequality 1, we see that this is actually less than or equal to P. But we also know that any R, given R, is smaller than R cap. And we have seen by the monotonicity of sub T composition, Q circle R will be smaller than Q circle R cap. But what is Q circle R? Nothing but P, because R is a solution of this equation, the relational equation. So from here what we get is Q circle R cap is both less than or equal to P and greater than or equal to P, which means this is actually equal to P. So what we have shown is that R cap is actually a solution, and also that if there exists some other solution, it definitely does not dominate R cap. So essentially we have proven this result, that the solution space for sub T composition, where the Q and P are fixed with R unknown, does have a solution if and only if this R cap, which is Q inverse delta P, is a maximal element of the solution space. Considering the same set of relations, moving from x cross y to 0, 1, y cross z to 0, 1, and x cross z to 0, 1, Let us now discuss the solvability of equations involving the in-phi composition. Once again, we are fixing Q and P and finding out all those R's which are fuzzy relations on Y cross X such that Q delta R is actually equal to P. Once again, we are in the setting of residuated lattices. The T and IT form a residuated pair. A similar kind of result as earlier can be shown. So now this solution space is non-empty if and only if, you see here, we are introducing the sub-T composition. Q transpose with sub-T composition P, which we denoted as R check, is an element of this space and it is also a minimal element of this space. What do we mean by this? A minimal element of this space means a fuzzy relation on Y cross Z such that it also satisfies the equation. First of all, it should satisfy this fuzzy relational equation, and if there exists some other solution to this equation, then that is definitely not bigger than R dash. So that solution is not smaller than R star that we are considering here. So this is the dual of the maximum element. Okay. Once again, we'll prove this. To prove this, we will make use of the other two inequalities that we have considered. So, what we have is S delta, which is set of all R element of F of Y cross Z, is that Q delta R is equal to P. Of course, the I here is IT. Now, the result says that S delta is not equal to 5 if and only if R check, which is given as Q inverse circle P, is minimal. Once again, the reverse implication is clear because if R check is minimal in S delta, it is also an element in S delta, which means it will satisfy the fuzzy relational equation, which means S delta is non-empty. Now let's prove the forward equation. Once again, we need to prove that if there exists, so what we are given now is S delta is not 5, this implies there exists an R such that Q delta R is equal to P. What we need to prove now is R check is smaller than any such R that we can consider. To this end, consider the second inequality. Well, what does the second inequality say? It says that R is greater than or equal to Q inverse circle Q delta R. But note that Q delta R is actually equal to P, which means this is Q inverse circle P. But Q inverse circle P is essentially R check. So what we have shown here is for any solution R check will be smaller than that, or at least R does not go below R check. So what we need to show is the second thing, that R check is in fact a solution. That means Q delta R check is equal to P. So let's look at what is Q delta R check. And this is nothing but Q circle Q delta Q inverse circle P. But now if you look at the first inequality, it is exactly the same, Q delta Q inverse circle P. We know that this is greater than or equal to P. But we know once again that the in phi composition, where I is IT, the residual implication, it is also increasing the second variable. Since R is bigger than this, what we have is Q delta R is greater than or equal to Q delta R check. But what is Q delta R? Because R is a solution to this, is greater than, is equal to P. So now what we have here is P is greater than or equal to Q delta R check greater than or equal to P, from which we get that is in fact equal to P. So that means R check is a solution and also If there exists some other solution, then it does not go below RG. So essentially we have proven that given Q and P, the conditions on R or the solution space, so that Q, you can find a relation R such that Q circle R is equal to P or Q delta R is equal to P. Well, we have looked at solutions of fuzzy relational equations so far, and we have seen specifically for the sup T and in-phi composition, because the context that we have set is coming from fuzzy relational inference, and we are interested in looking at interpolativity there. We have seen that residuated lattices play an important role. At the beginning we asked, is the role of residuated lattice over? We have seen that in fact residuated lattices, with the powerful, the rich properties that they have, the rich structure that they possess, they are able to supply us with all the properties that we require to be able to prove some key results. Oh, what next? We would like to discuss interpolativity in the case of multiple seesaw rules. This is the link part that we have actually discussed. As was shown in one of the slides earlier in this lecture, if you want to discuss about interpolativity, we have this set of rules, the antecedents and consequence, AIs and BIs. If you take them to be matrices Q and P, what we are interested is in finding an R, such that when you give these rows, essentially row-wise composition should give a corresponding row. That is what we are interested in. And in the context of FRIs, we are interested only in sup T and in-phi composition, and that is what we have discussed in this lecture. The solvability of fuzzy relational composition, fuzzy relational equations, when the compositions are essentially sup T and in-phi. However, the T and I, they actually are related to each other as a residuated pair, so they come from a residuated lattice structure. In the next lecture, we will make use of these results discussing the solvability of fuzzy relational equation and see how we can relate them to the interpolativity of the corresponding FRI, whether it is a compositional rule of inference or the BKS inference. This we'll take up in the next lecture. A good resource for that deals with fuzzy relational equations itself, specifically what we have seen in this lecture, is the book by Antonio Di Nola, Salvatore Sessa, Pedrich and Sanchez. It's an edited volume. We would also like to highlight some seminal works which are related to fuzzy relational equations. The one by Sanchez way back in 1976, and also the work by Pedrich way back in 1983. See, thus, these are two seminal works which dealt with fuzzy relational equations, and as you can see, they also give an inkling as to where they can be useful. So, glad that you could join us for this lecture. Hope to meet you soon in the next lecture. Thank you all.